In this lecture, we'll cover solar cell as optoelectronic device. Why do we call solar cell as optoelectronic device? Because one, that it is based on the optical signal in the sense optical input, I'll say, that is the light energy, and it has semiconductor electronics, conductors in its manufacture. So it is an optoelectronic device in that sense. What are the characteristics which we need for solar cell? In solar cell, what we want is that light has energy in terms of photons. We want to utilize this energy by some mechanism. This is that mechanism, some mechanism which, when receives the photons, generates voltage difference, or I'll say the current. It generates current. This is the mechanism we want. So this mechanism is obtained by skillful use of these semiconductors. What we do is we take a P-type semiconductor, which is silicon. P-type, it is silicon. Silicon because we need the semiconductors having energy gap in the range of 1 to 1.8 electron volt, and silicon has energy gap of 1.1 electron volt. And why do we need this range? I'll also come to that. So we take a P-type semiconductor having thickness of 300 μm. On this, I'll make it slightly thicker, as on this a thin layer of N-type semiconductor. This is P, and we have on it N-type semiconductor, say 0.3 μm thickness. If I make it three-dimensional, it will be like this. It will, if you have a three-dimensional look, it is like this. This is the junction boundary, and we provide a base plate. There is a base plate here which is connected to a conducting electrode, and we also have an arrangement where these electrode plates are embedded here, and this is the output. We can connect this to output. This is the basic structure. Now what happens in the solar cell? When the light falls on it, if we look at the schematic diagram of this junction, this is P, this is N, this is the junction boundary. We know that there is a depletion layer, and because of which there is a positive charge on this side and negative on this side. This causes an electric field like this. This is the electric field in this direction when there is no bias, and it is a equilibrium condition. This is the direction of electric field. When the photons strike this junction where you have an transparent opening to allow the photon to strike the junction region, that is the depletion region in and around the junction boundary, what happens? If you look at the energy band diagram of semiconductor, there is a conduction band, there is a valence band. Photon which has energy of more than 1.1 electron volt can easily excite electron from the valence band and it goes to the conduction band. So hole is created and electrons. So you have EH pairs for the silicon crystal, and when silicon crystal, when the photons are falling on it, EH pairs are generated. In any semiconductor, in the doped semiconductor also, the EH pairs are constantly generated and destroyed. But when you have an electric field due to the doping, this electric field across the junction, if the EH pairs are created in the junction region, EH pairs created in the junction region, E and H, and the direction of electric field is like this, the holes move along the electric field and holes move like this, and electrons move like this. So there I am showing a magnified view. Suppose EH pairs are created here. This is the direction of electric field. Holes will cross over in this side and electrons will move in the opposite direction. So there are three stages. One is generation. Generation we have seen, EH pairs are generated. Then there is separation. This is because of the thin depletion region, high electric field. These EH pairs are not allowed to recombine. This electric field separates them and E and H pairs move in different directions. Then is collection. When you connect it to a load, to a circuit, when you connect it to a circuit, say this load, the current flows. That is, the holes which have come to this side, electron come to this side, result in generation of current, and there is a voltage drop across the resistance. So you can generate the power using combination of large number of solar cells. Now the other aspect we need to know about the solar cell is, why do we use silicon? Why do we prefer silicon? Of course, we generally prefer silicon and GaAs. There are various types of other material, say CDS, PBS. We prefer these two as compared to these. Why? We will understand that if we draw the irradiation, the intensity of the light of the solar radiation in comparison to the energy EV, electron volt, we find that at 1.5 EV energy of photon, this energy it is the maximum, means intensity is maximum for this energy gap. You have different, means solar radiation doesn't comprise of single energy. It is not that all energy is in 1.5. You have different levels. There is greater than 1.5 also, but the maximum radiation has 1.5 EV. So the majority of the radiation has 1.5 EV. So if we are able to exploit this region around 1.5 electron volt or less than that, then we are able to utilize most of the intensity. So the utilization of solar radiation is more optimal. So that is why silicon, which has 1.1 electron volt, is preferred, because you are able to exploit greater intensity of solar radiation. Gallium and arsenic has about 1.53, I think, maybe in that range of the energy gap, but since it has higher absorption coefficient, absorption, so it can be preferred against silicon because of the higher absorption. So this is also used. Now take the case of CDS. CDS has energy gap more than 2 electron volt. I think it is about 2.4 electron volt or so, but it is more than 2 electron volt. So you do not get, if you go to the higher electron volt, you are unable to utilize the energy, lot of the intensity which had less energy, less than 2.4, this large amount of intensity of light we are losing, and we are able to utilize only the small part. So there is no efficiency as compared to silicon. Now PBS has the energy gap of 0.4. So one may say, why don't we use this so that we are able to utilize much larger region? All this region having more than 0.4 electron volt, we will be able to utilize the entire radiation spectrum and have more efficiency. But the problem here is that with low electron volt, most of the solar radiation is absorbed before the junction region. So lot of solar radiation is lost in the region which is outside the junction region, in the top layer. If you look again at the diagram, this was P, this was N. Solar radiation is falling like this. So in the top layer, most of it is absorbed. EH pairs keep on generating. It keeps on generating EH pair, and they are continuously destroyed. It doesn't help. What we need is generation of EH pair at the junction boundary. With very low band gap, most of the solar radiation get absorbed here only. But we want solar radiation to reach here, and in this region we want EH pairs. That is why PBS is also not used. So this was just the basic of the solar cell as a optoelectronic device. Thank you.